Well, you see, I started my life with neutron scattering area, neutron diffraction, neutron inelastic scattering. I spent 18 months at Chalk River in 1956 to 58. We did some pioneering work on excitations in solids, especially lattice dynamics, with Brockhaus. We eventually got the Nobel Prize in 95. I came back and was using the reactor Cyrus for neutron scattering experiments. Built up the laboratory, built up the equipment, built crystal spectrometers. And then of course in 1968 we got interested, in fact we went on a mission to Soviet Union where we were excited by looking at the pulse reactor at Dubno. That is the time when you can get pulses of neutrons from making the supercritical for a short time. That is why we came back and we decided to build a critical facility and simulate the effect of reflector on this fast critical facility. That is the Purnima reactor.
I briefly mentioned to him yesterday.
That is where our interest in, my interest, personal interest in fission energy started off. Because we were also planning to build a new center in Kalpakkam on fast breeder reactors, for which I was one of the members of the physics community. We wanted to put up this pulse fast reactor at Kalpakkam. So he was the reactor physicist who made all the calculations, made the system go operate. Then of course came this announcement that nature has not restricted nuclear energy to fission energy. Of course, Homi Bhabha always said, as long as there is deuterium in the seawater, there will be no dearth of energy in the world. That is from the fact that
You said start from Homi Bhabha, what he said?
Homi Bhabha was elected first president of the first conference on peaceful use of atomic energy under the United Nations. Homi Bhabha, to put you in the right perspective, was a contemporary of many Manhattan scientists at Cambridge University in England. He was in the Rutherford laboratory, he did his PhD there, and therefore most of the people you can think of, whether it is Tom Morrison or D. Hoffman in General Atomics, they were all his colleagues. And he came back to India just before the war and got stuck. He couldn't go back to Cambridge to continue his research. Otherwise, he was a cosmic ray physicist, and he decided to build an institute for nuclear science in India. And in 1945, he wrote a letter to the government, not the government, the Tata Trust, saying that I want to start an institute here so that nuclear energy becomes feasible. You will find the experts at home. That is in 1945, before the nuclear power reactors ever was built, and even the nuclear bomb was not exploded at the time. Anyway, Homi Bhabha's friends, like Richard Garvin, for example, was a friend of Homi Bhabha, who did this mic explosion. That created the feeling in Bhabha that fusion is indeed feasible. The only problem is that how do you do it in the laboratory? Therefore, he made the prediction in the first presidential address in 1955 that in 25 years' time, scientists may find a way of producing fusion energy. Anyway, in fact, Homi Bhabha in Tata Institute organized a plasma physics group for the first time because he heard that eventually fusion will become feasible by working on plasmas. An Imperial College had a small group on plasma physics. He made a man called K. George build a plasma device. He made this prediction in 1955 because people thought, oh, he was talking through his head, that it's not feasible. But soon, by 1958, the second Geneva conference, the Russians came out with the tokamak idea, and the British were conducting Z-pinch experiments at Harvard, right?
Yes, I mean they had a whole session.
And that is how our interest in fusion. But it was quite clear at that time, the technology required to do this thing is very involved.
The fusion.
And therefore, we have got to start from scratch. Do with small plasmas and then graduate to a tokamak system. And but our aim in 1960s and 70s was BARC will concentrate on fission energy. Dr. Ramanna was our boss. He was himself a fission physicist, and we started work on basic physics of fission, and we built this Purma reactor and got interested in the fast breeders conversion to thorium to uranium-233. Built a uranium-233 reactor, Kamini at Kalpaka, which you probably see. Natural reactor, because the uranium-235 percentage was higher in those old
It is an amazing discovery that millions of years ago, there had been functioning a natural fission chain reaction lasting for another million years.
What was the structure of this reactor?
Natural
Uranium mine
uranium
with water.
Oh.
But in those days, the enrichment of the uranium was sufficiently high, not the 0.7% today, but 3.25%.
Right.
So it was an amazing discovery for mankind. It was really hitting headlines in those days.
In fact, Weinberg visited that place, and his remark on the television I saw was, I was always disturbed by the fact that we discovered fission, which nature had not demonstrated. But now I see that nature has already demonstrated fission.
That's a very fascinating concept.
And I am satisfied that after all, man has only been doing research and rediscovering what nature has brought out as nature's laws.
Very interesting.
Very interesting remark he made at the time.
So where did we leave off in your history of this?
No, but as far as then of course in 1974 we had this first explosion, Cochrane explosion, in which we all participated. That is because we were the core group who were doing the physics of fast chain reaction, and obviously to extend that to a calculation of what happens when you have only plutonium-239, what reflector, what trigger, etc. That was done in 74. And following that, of course, he continued to build up the Kamini reactor, which used the uranium-233, because by that time we had irradiated thorium and got sufficient quantity of 233 to build a reactor of its own. We're using it only 233. That was about a few kilowatts, just as a neutron source. That has been set up at Kalpakam because that is the place where fast reactor work is being done. They wanted it for radiography of fast reactor fuel. This small reactor is inbuilt in a glove box so that the fuel element can be brought there after the radiation levels, things like that. After all, Homi Bhabha said some method will be found for fusion, and maybe this is it. So we put a lot of people to work on that area, whether it is chemist or metallurgist or engineer or physicist. Pardon?
About how many people did you have working on the research?
You see, BARC has got what, 5,000 scientists. Okay? So, it is easy for us to ask the metallurgist to make, palladium, or soak palladium in deuterium. For example, we did titanium and deuterium. Yes. We want titanium, yes, we have a metallurgy group which will give us titanium. You want electrochemist, yes, we have chemistry people who do electrochemistry. We had heavy water people who produce heavy hydrogen gas out of electrolysis. So it was rather easy, and of course it helped because I happened to become the director, and therefore we could make everybody.
You choose people to get involved.
So
you were the director of BARC at the time?
I was director of BARC at the time. 84 onwards I was the director of BARC. To some extent that did, I couldn't spend too much time on the experimental side, but he looked after all that. Yeah. Well, what else you want to know about it?
Well, actually, I want to go back just a little bit from the history. Can you say again that the Nobel Prize that you achieved?
Well, that is because...
What was that?
That is because in 1956, when I went to Chalk River, Brockhaus was a lone man. He was a very clever physicist, very young for the group there, and he decided to look at the neutron analog of the Raman effect. In Raman effect, you are using a light scattering, and it picks up the molecular vibrations and comes out with change in light wavelength or energy. But he could do the same thing with neutrons. If you knew the initial energy and the momentum of the neutron, that on scattering it changes both the momentum and the energy. And if you measure that, then you can directly correlate with excitations in molecules, solids, things like that.
Okay.
So he was building a spectrometer in which you first initially monochromatize, that is, make it single energy of the incoming beam from the reactor, scatter it from a sample, which is a single crystal, and then look at the energy and the momentum of the scattered neutron. If you do that and just write down the equation for momentum conservation, energy conservation, you get the excitation, momentum, and the energy. Well, that is one of the fundamentals that are required in solid-state physics. So he decided to set it up at Chalk River. Surprisingly, the United States had many reactors of equivalent or same flux, like Brookhaven, Oak Ridge, and Argonne. But this man, because he was starting research from a freshman from a PhD, he decided to concentrate on this. And he succeeded. And that was the time, 1956, when Chalk River started working on that. And I happened to be sent
young
to
man.
I was also young, I was only 24 at that time. So we worked together and we hit on a good problem of looking at the vibrations of germanium crystal. We could get a crystal from Bell Lab, who are making a lot of germanium crystal.
You worked from March 1989.
March 24th morning, he saw the Times of India news item,
Yeah.
4 lines, like Mike too must have.
And you worked for a period of what, 2 or 3 years?
Yeah, more or less.
What are
No,
your-
more than that. I think went on.
He moved on, but slowly petered out. It was not-
Well, I moved out as chairman of the Atomic Energy Commission in 90. So, but he continued the work here. Of course, I could also come occasionally and spend time. But
Can you share with me like a couple of unique moments that you remember during that time?
yes, we had probably what, 10 different groups looking at it.
Yes.
And therefore, when I get a call saying that we saw neutrons or we saw tritium, it was exciting. So I could come and spend time. For example, we put a number of titanium chips and put it in a chamber, vacuum chamber, putting helium,
Right. Liquid nitrogen.
liquid nitrogen, and deuterium. And after some time, you notice that we count for tritium, and one of them became
4 out of 1,000.
1,000. Okay, one piece out of several things that he had put.
And even though it was only 4 out of 1,000, was that encouraging?
But those 4 gave such a fantastic
Such a
amount
fantastic,
of
right.
tritium. Any fool could see it. You just stick it in front of a germanium or Geiger-Müller counter, you see the beauty about tritium in a titanium lasted as against tritium in a palladium is the following. My memory is correct, the 23 keV
Right.
beta particle
Beta particle.
of the tritium decay was able to excite the titanium K alpha line.
Right.
You get a beautiful X-ray peak. So you can demonstrate, even though the beta particle cannot come out of a gamma counter sitting on the peak, you could demonstrate beautifully.
The chance of getting such high activity was only 1 in maybe 1,000 pieces. Clearly shows that there is something unique about the titanium lattice and the metallurgy of that, which made that particular piece.
This is what I learned in that experiment.
Right.
We took a titanium rod,
Yeah.
took it to the machine shop, and
Turned
got shavings. In the process, there was a lot of damage, lattice damage that was created. And I think this rough edged pieces somehow created conditions for a titanium deuteride in that spot to give rise to reactions. I mean, they giving us a clue.
Why he takes an interest is because now it's quite clear that the metallurgy of titanium and the kind of defects, the kind of things that
Or palladium, titanium or
palladium or something, are important from the point of view of cold fusion. How you are able to get high density of deuterium,
Right.
okay, which is to bring deuterium close to one another. Okay, this is probably a metallurgical way of doing that. That's what this experiment demonstrated.
What
And
Mike and
I'm
others
sure
have found. Yeah, exactly.
Yes, experts. They are experts in that.
So how about any other highlights? So besides the
Well, that is, we had, for example, a commercial electrolytic cell which was made, which was
I was
bought
telling him
over
about the Milton Roy cell.
Milton Roy
One of
cell,
accidental.
which is commercially available in America. And he just took it over and then found that he can produce tritium in that.
As I was mentioning, it is remarkable
Yeah.
that on the day we saw the March 21st, on my table was a palladium D2O cell right there operating, producing deuterium gas. But we were doing it because we wanted the deuterium gas, pure clean deuterium gas for the plasma focus experiment. So it just need us to bring in the neutron detectors. And
in the years that you were, the few years that you were doing the research, did you see any progress, or was it always very challenging? Were you able to?
Yes, in fact, the wide variety of experiments which we did involving chemists, electrochemists, metallurgists and physicists, it was quite clear to us that, look, we don't know the reason. That is why we are looking at it from a different pathways to find out the effect. And if we had proceeded on that basis, I am sure we would have hit the, just like in what is it, Los Alamos, you had storms, right?
Storms was there and
And that storm had a tritium production cell, isn't it?
Yeah.
In fact, he offered to make tritium for the American nuclear weapons program instead of wasting money on the accelerators.
That part I don't know. But I understand Tom Clayton is still working outside the
Slowly,
Los
yes.
Alamos lab. Still
Anyway, the
using-
point is, it was interesting because I did make a mention of this thing. There was a British scientist who visited New Delhi, and somebody asked him this question: if it produces tritium, what do you think is the future of non-proliferation? Then he said, "Oh God, don't ask me this question. A garage will become a hydrogen bomb source." I mean, this remark was made by Harvard scientist who had visited New Delhi at the time, around that time. Now, the other important aspect is, it was also demonstrated by us that the tritium yield was certainly much more than expected from this DD, the two pathways that you have.
The branching ratio anomaly.
The branching ratio anomaly, which of course is Texas A&M also proved the same thing. If that happens and you get a neutron source out of this thing, out of this reaction, it would change the fission reactor technology, because now you could substitute a neutron source almost anywhere in the core. One of the burning problems of fission reactors today is, can you produce more fuel than you burn?
Right.
Okay, and the approach has been advocated right from the Manhattan days, is to have an external neutron source which would be a fissile material factory. The Oak Ridge National Laboratory has built the first, what source is that? What reaction is it? GeV proton.
Spallation neutron.
Spallation neutron source. But the spallation neutron source is a point source of neutrons. And reactor physics says, like what Kohler demonstrated, if you had a seed and blanket distributed in the core, that would be a much better breeding reactor than a point source, neutron source. So in fact, the advanced spallation neutron source would fail unless they discover methods of making many targets inside the core.
So these thoughts were along the lines of what if
so
fusion
if
produced
the
neutrons?
fusion, the cold fusion succeeds, then you could distribute it inside the core of the fuel.
That's if it succeeds as a neutron source. Okay,
as a neutron source.
We know it's not.
I think the beauty of fission is we discovered that you get 2.5 neutrons per fission, out of which 1 is required to sustain the reaction. Out of the 1.5, you are able to get at least 1 to convert thorium or uranium-238 into plutonium. Then it becomes a self-producing fuel factory.
You saw that it didn't produce many neutrons. You got some significant tritium.
Yeah.
What are some of your other recollections about that other early time?
Well, and the energy production, heat production.
Did you do much heat measurement?
Yeah, we did a lot of heat measurements. In fact, there were chemical engineers who measured heat production and calorimetry.
Right.
I think they were successful in doing heat production, right? The calorimetry of...
Not very much, I must say.
A little bit with that Murthy or what's
Yeah, some people tried, but
But we did not concentrate on that. We were more on...
calorimetry.
Because the heat was and still is such a significant part of the whole phenomenon, what was your early reaction to the idea that you could possibly get some useful heat?
If you personally ask me, I thought that this may not be an effective neutron source compared to the total energy produced per fission in uranium. So that's 200 MeV.
Right.
Okay. Here we are talking about a DD fusion of 14 million volts around.
No, DD is only 2.5.
Sorry, DD is 2, but DT is 14.
Yeah.
So you are in the lower range. However, the fact that it produces one neutron, which is a 14 MeV neutron per fusion, or 2.5 MeV.
In this case, only 2.5.
2.5. And if you can use that to supplement the 2.5 neutrons produced in fission, then you will have a combination of cold fusion plus fission, which would increase the energy density as well as the availability of neutrons. In fact, that's what I was coming to. If 1.5 neutrons are used to breed, you get only less than 1, because there are leakages, there are absorption, etc. Now, if that could be supplemented by cold fusion, then of course you have a system which is breeds even with light water coolant. That will completely change the picture. I mean, it was only Rickover who proved that light water reactor could also come as close to breeder as possible. I don't think.
So what you say is our initial interest and excitement was the possibility that here is a beautiful neutron source which will fit into conventional fission reactor technology very well.
Right.
But it's a different matter that we learned that the neutrons are very little and it has no correlation to fission reactors.
Right.
No, we never thought that it is going to be much cleaner than that of fission reactor.
Oh, really?
Because you are producing tritium and you are producing 14 MeV neutrons.
That's right, because you knew very early on that it was producing tritium.
But on the other hand, even now, I still believe the tokamak people, on which $10 billion is being spent internationally. Is it useful to do this? Because we have never demonstrated the geometry of a ITER or a tokamak as an ideal geometry for breeding. You have got a superconducting magnet which holds the plasma together. But on top of that, you have got to put a breeder with thorium. And how effective this is.
They are not doing thorium, they want only graphite.
No, but then our interest is...
Our interest was there. Yes.
Okay, now Livermore insisted on a linear plasma. Because I remember listening to them, that geometry allows you a breeder concept. You can easily put a breeding
blanket around
that. Whereas tokamak, that way is not very good. Okay, now here again, a set of scientists went to IAEA. IAEA, there was a man called even Abdus Salam. He propagated the idea that you should do plasma physics. He published a journal called the Plasma, right? Fusion. Fusion by. So they decided that we should have an international ITER project. This year, Bush has stopped, cut down.
You heard about it.
Yeah, I mean, he is doing wrong things. I mean, the Fermi lab, 200 people are going to be sent out or something like that. He is announced something. Anyway, these are all.
Sani was telling us, Dr. Sani is unable to join us because there's a team coming from Fermi lab begging BARC to please take over this. We don't have.
I perfectly agree that we should collaborate because we have a large manpower and we can create this large manpower. We have the capability. But what is happening in America is the American science, especially in nuclear science, was built up by migrants from Europe before the war. Then came a lot of West Europeans who couldn't get a job after PhD in Europe because they were rebuilding the country. So they moved to, even Germans and French.
Okay.
If he did a PhD, he would come to America and become a university professor rather than be there. But New Zealand, for example, Australia, after all, the British science was built up by an Australian called Bragg, right? Bragg is an Australian, right? WL and WH Bragg.
The Bragg, X-ray diffraction.
Yeah,
okay.
X-ray man.
Bragg.
Rutherford was a New Zealander, isn't it?
Yes. He mentioned the history.
Right. And I know my friend Graham Lowe from New Zealand. He became director of Harvard. He's a good friend of mine. He used to pass through Bombay many times. So that way the manpower, sharing of manpower in the world, in frontiers of science, has been going.
You and your colleagues, there was a lot of skepticism about it, there was a lot of uncertainties about it. What was that like for you talking to your colleagues from that perspective?
There was no difficulty at all at that time because everybody who participated in that were willing to take the risks associated with something which is not theoretically proven. It was an experimental approach because some people in US have done that, so why not we repeat that and find out whether we can make headway on that. So that is where this thing happened. However, the question that you are leading me to is to say, was there an influence from America to stop this kind of work? This happened after I retired.
After you retired?
Right. I think there is a chap called Devendra Lal. He's a geophysicist. He was originally in TIFR, was looking at radioactivity due to cosmic rays and things like that. He came and he said, look here, the Americans, physicists in America, feel that anybody who does continue to work on cold fusion is bringing bad name to the lab. Why are you doing this thing? I said, look, you shut up. We should know what we want. I don't go by what somebody else says.
No,
I told him.
Historically, he wrote this letter to you or to Dr.
He didn't wrote, he came here.
No, but there was an email. The word institutional support was there.
Yeah, I know. The point is that he told me, he came here and he told me that, look, why do you do that? And there's similarly C.N.R. Rao, who is a very influential chemist, was a colleague who knew, not Chidambaram, this man in Texas, what is his name? Bokris. He had gone to Bangalore and worked with
Amulya Reddy.
Amulya
Reddy was the co-author of Bokris.
Electrochemist. Okay.
Well, let's not take names.
Okay, so this gentleman, he said the physicists in America were upset about. Were physicists in India also having the same perspective?
The one thing that was very clear at that time, I think he will hold my hand, we were very dominant in physics community in India. If you talk of BARC, there was nobody who could raise a finger at us at that time. Right? In anything that we did. Therefore, once we were several groups in BARC were working on that, nobody could have stopped us.
Okay.
Okay. However, those who do this postdoc and come back, they get influenced by brainwashed.
Go to the US.
Who go to US and come back.
Okay.
They get brainwashed. Those who depend upon, so let us say, project allocations,
Funding.
collaborations,
Right.
they got brainwashed. Oh, what is it? I mean, like our friend Kapoor, one of my own assistants. He was a student of
Iyengar.
yeah.
No, student.
No, student of this man, Rochester man.
Iyengar.
Iyengar.
He would swear by Iyengar.
Right.
Okay, then so Iyengar went against it in that Washington meeting.
And wrote.
So he will get used to that. So I said, nothing doing, we must have an open mind. It is not one man's show here. Anyway.
That's very interesting.
Anyway,
to
I think that's all past.
And to some extent, I think my successor also got influenced by that.
You know.
But unfortunately.
Well, it's very interesting to me to hear how the perception of it evolved in the Indian scientific community, because I know how the perception evolved in the American scientific community, and I can hear that.
This is exactly the subject. I spent 3 hours with that Ferguson on Sunday, or not, 3 days back he was here. He is writing a book on nuclear energy. I spent 3 hours explaining to him how you misled the world, US, on nuclear energy. For the first time he is hearing somebody who criticizes the United States. You have the picture that, oh, anything that can be done has been done in the US. Look here, you went into a light water reactor because of the submarine. You had money in defense. You had enrichment capability. Then you gave it to commercial exploitation to Westinghouse and General Electric. And they closed down their efforts in UK and France and Canada. But the Canadians could not be moved because Louis was a very strong man. That is why the Canadians pursued the heavy water reactor. Whereas the French and the British succumbed to this pressure from for light water reactor. In the 1982 meeting on Neutron in Cambridge, I was there. Lord Marshall was then
on the occasion of the 40th anniversary.
50th anniversary.
Of the discovery of the neutron.
Of the neutron. Okay? One man, the old Cambridge group chap, asked a question to Lord Marshall, who was the chairman of the atomic energy. Why is it you can't follow the heavy water reactor, which after all our friend Louis from Cambridge who went to Canada has propagated and has successfully demonstrated? You know what his answer was? He said, look, it will take me 5 years to get the clearance from the regulatory authority if I want to introduce PHWR. And we can't wait till then. He came down from the stage. So I went in and said, what stupid answer did you give? Because he was your colleagues in neutron scattering at all. Then he said, look here, I've got to save myself. As if to save yourself, you say this. Hans Bethe, he openly said the Canadian approach is extremely interesting and is good. They have demonstrated that you can do with natural uranium, heavy water reactors. Unfortunately, it produces plutonium more efficiently than your light water reactor. But then the world must know how to live with it. This non-proliferation lobby in the US, which says stop any other country from being able to produce fissile material like plutonium or uranium-233, is bound to fail because it is against the basic laws of physics. The basic laws of physics says that if you have uranium-238, it will produce plutonium. If you have thorium, it will produce U-233. And since the percentage of uranium-235 is only 0.72, and you enrich it to make light water fuel, you are burning less than 1% of the uranium that you mine. The rest is all going as ballast for the airplanes that you build. Uranium-238, depleted uranium, goes to the weight, balancing the weight of the plane. No, why are you misleading this world? If you had a technology like the fast breeder, which produces more plutonium than you burn, then of course you would use the 100% of the mined uranium. and not this less than 1%.
Do you have any ideas on how the world should respond to that matter of creating plutonium?
Right. So, then of course the counter argument is, we have watched UK went ahead and made their bomb, French went ahead and made the bomb, the Russians independently, in spite of the fact Truman said, look, the Asians will take a long time to make the bomb. They did it in 2 years. You remember 47, 49, they made the first bomb. Okay. Similarly, the North Koreans were able to make the plutonium. Right. Iran will probably enrich it. And perhaps will have the technology for the plutonium. So, you are attempting to do something which is impossible. And there is no forward thinking in the US scientific community. Tell blindly the government, look here, this kind of a control is not going to succeed. In 1995 or something like that, there was a man called, a diplomat called Kennedy. I don't know whether you remember him.
Many Kennedys.
He was representative of US in IAEA.
Okay.
He was assigned the responsibility of talking to South Africa, Brazil and Argentina to bring them into the non-proliferation treaty fold. So he went and offered billions of economic aid and things, right? Finally brought them, in spite of the fact that the South Africans, along with the German assistance, produced their own uranium-235 for the bomb. They had 5 bombs sitting there. The Brazilians made their own enriched uranium. In fact, they have a technology which is better than the American and the West European technology for enrichment. There is Argentinians who did the reprocessing. I myself have seen that factory. Facility. Okay, but the government they were able to influence the government, saying that if the economy is in bad shape, you fall in line, we will give you the assistance. The Brazilians dug a hole in order to test the bomb. The man called Goldenberg was the vice chancellor of Sao Paulo University, became a minister for science. He was present when they closed that hole.
I think perhaps the reason why Triangle is bringing all this, I don't know whether this is right. There is a possibility that the result of the US Department of Energy report might have been influenced by considerations other than scientific. Someone somewhere felt it. This is something that even Martin has probably hinted at. It's not a scientific evaluation.
I told you this.
They decided in advance that we have to.
You openly said, look, if it is proven that coal fusion is indeed feasible with an electrolysis, and you produce tritium, God help this world.
What do you propose? Do you have any ideas or proposals for how the world could or should respond to take advantage of the peaceful uses of it?
No, who is going to lead this? It is not that you haven't let Eisenhower, as President of the United States, had the Atom for Peace policy, in which he spent money on educating people from developing countries on nuclear science, distributed research reactors, so that the technology of use of radiation in health, agriculture, research will spread.
Okay.
That is one part of the story. But at the same time, now, you say, look, all such reactors, core must be withdrawn because they use more than 20% enriched uranium. This may become a source for bomb material. Billions of dollars are being spent in withdrawing this thing. The General Atomics, which made money, commercial money, by making the, Trigger mark reactor, cannot anymore sell these reactors because that uses enriched uranium which is higher than 20%.
If you could tell the people of the world how to take advantage of this possible new nuclear technology.
No, this is not a purely scientific question. The question comes in, can you stop science from making its own impact in any society.
Okay, understand.
Okay? You take the North Koreans. They send a few people to Dubna, to Obninsk, Moscow, Kurchatov Institute, etc.
And also BARC.
And well, they didn't work here. They used to visit. They didn't come here. They came here once, I remember, 74.
Yes.
But then we did not have any strong interaction. But then that was sufficient for them to have a test tube kind of technology for producing plutonium. The 5 megawatt reactor which the Russians built in 1954 in Moscow, in Obninsk, they had worked there, so they copied a similar reactor in Pyongyang or whatever it is. Okay?
So what you're saying is...
What I am saying is, you cannot stop the spread of science. It is the good sense of the political party. You see, this is where you should see, India is only country in which there was a man like Mahatma Gandhi, who said, even if you want to fight your colonial dominance of England, do by satyagraha,
What is
by renunciation,
Non-violence.
not by violence. We still hold the view, we are not making the bomb to attack somebody else. We are doing it in self-defense. Because you recognize, the world recognizes a strong person. So we had the Pakistan. The Pakistan we knew right from 1974 when we exploded the bomb. This fellow, Abdul Salam, who was the head of the theoretical physics in Trieste, had come here to my office and he said, look, can I leave this thing here? I am sure you have got material about the bomb. I said, look here, I don't keep them here anyway, don't worry. Okay, now he was at Zali Zulfar Bhutto. He called him to Karachi and asked his advice. His advice was, make more basic scientists. That is the only surest way of your achieving success.
Got it.
Okay, and then he it fell on deaf ears because when he was succeeded by that military chap, what his name? Haq, isn't it?
Yeah, Ziaul Haq.
Ziaul Haq. The Munir Khan is a good friend of mine. I have gone and had dinner with him at his home. He was the chairman of the Atomic Energy in Pakistan. He went and asked him for 100 PhDs. You allow me to recruit 100 PhDs. Then he said, where are the 100 PhDs in Pakistan? Unless you withdraw, bring back people who are doing their PhD work abroad. Munir Khan told me that the Pakistani students were not even taken in PhD programs in the US because of the fact that they are threatening to have their own program of atomic energy program. Anyway, so
I got that.
good sense has to prevail. We must have spokesmen which say this atom bomb is useless. And you don't say that. What is the name? Clinton. President Clinton advocated CTBT. We also went along. But then eventually after spending billions of dollars, getting almost a unanimous opinion of the rest of the world, he signed the CTBT, but your Congress did not ratify. He threw it out. Which means the conscience of the United States is not for being liberal with the rest of the world, but being dominating in the rest of the world.
I applaud your speaking.
Okay, now if that happens, then we have got to be careful. You make peace with China. When we said China, you have to recognize China in the 1950s and 60s. When Nehru used to plead for China, they said, oh, this man is a half leftist. Then what did you do? Kissinger flew from Pakistan to Beijing to make peace, when they were throwing millions of people as refugees into our country from Bangladesh. When democracy did not operate in Pakistan, a democratically elected prime minister was thrown saying that you come from Bengal, you can't become prime minister. That is what created the war. They all said, look here, this is a dirty word in America, don't touch it. Going on for a long time. It's one of those frontline international projects in the high energy field. When the United States started that project, our scientists who work in Fermi Lab suggested to me that, look, we should become partners at this stage itself. This will give us cooperation in technology, and also it needs usage in frontier areas in particle physics. So I decided to approach the Prime Minister, and he asked me the question, what do you mean by partnership? I said, look, it is not going to be partnership of just by labor, but it's a question of some investment. We can make a token contribution of $50 million in the next 5 or 10 years when it is being built. Most of it will be done by equipment made here, which are not so complicated, but we can do it ourselves and supply them, so that we can write it out. He agreed. So we signed an agreement on the SSC project. I went and attended their council meetings, etc. Unfortunately, 3 years later, the next president said, look, no more SSC project. You have dug a hole which is half of 60 kilometers, half of 60 miles, but then you stopped everything. I was aghast. After spending $2 billion, you abandoned a project of that time. We had sent, even by that time, 20 Indian scientists, right from civil engineers to cryogenics, modern cryogenics of helium, liquid helium.
Okay.
They came back and became part of the CAT. But still,
it's a center for advanced technology, I was mentioning before.
Right. Okay. But this is the way we wanted to cooperate. What we have is a limitless manpower, which we can generate. Last October, I was in San Diego. I went and visited General Atomics. The director of that, who came from Livermore, was a retired man from Livermore. He said our main problem on this thorium utilization is manpower. Today we switch back to the nuclear power. We don't even have manpower.
Wow.
When I said how many do you require? How much can you give? There are 250 engineers retiring every year from BARC and NPCL. I am sure 200 can easily be spared, because after retirement they don't get similar jobs here. Then he thought, that's a good idea, we should make an arrangement so that until from 60 to 70 they could contribute. Now, this is the way we should be able to cooperate.
Well, so there was a point in time when the research in cold fusion at BARC slowed down and stopped. What are your...
That is after 93, right?
No, 90. More or less, immediately after you
After,
more or less, started.
No, but then even then
Yeah,
you were able to
slowly.
continue.
The process started,
Yeah.
and by the time you retired, it was almost completely.
Right. Well, I would say that, look, I think we have to accept the fact that just like superconductivity took some, 40 years to get a theory to back it up. Experimentally it was proven in the early 1910. But then it is only by 1960 that you had this BCS theory explaining that. Similarly, we are in the cold fusion also. I don't know, you may know better, that we lack some new ideas or some new method of explaining this. And until that is reached, you will have this problem of people saying that, no, these are all, what is it Morrison used to say? Pathological science.
You think that...
I know him well.
Do you think that theory will, an accepted theory will help us significantly?
It will come. I'm sure that it has to come and it will come. Only thing is, that requires a little lateral thinking, not necessarily textbook type kind of derivation. And if that lateral thinking has to come, the more the number of people who indulge in it, the greater the chance, the faster it is.
Could you elucidate just a little bit what you mean by lateral thinking?
What I mean lateral thinking is, you do unconventional thinking. Like for example, you talk of mega-Gauss magnetic field. That is magnetic fields which are
million
Gauss. Many things occur. But how do you generate this mega Gauss? The first time I read about it or heard about it, if you knock a single electron from the K shell and make that out of the pair which is spin coupled, one of them off, it produces a magnetic field of a mega Gauss at the nucleus. And the way it was measured was that this mega Gauss magnetic field immediately acts on the spin of the nucleus and splits energy levels by a very small energy difference. And you could do Mossbar effect. The energy involved in that is in lateral motion of velocity of centimeters per second.
Okay.
And detect this splitting. Okay. Now imagine this mega Gauss technology being used in a bomb in order to cause fusion or pinch the plasma to such high density to make a fusion possible.
Okay.
That is probably what is happening in the Z pinch.
Yeah.
Okay. Now, so this lateral thinking is what I call that you have to borrow ideas that has been demonstrated by somewhere and say whether this is applicable to somewhere else.
Understood. Very good.
Isn't it? So, like that there are innumerable ways. Today you take biotechnology. What nature has done by proteins, by special devices.
Enzymes.
We are not being, the chemical engineering that we do is nonsense.
Yeah.
The plants are sensitive to fraction of a degree.
Right.
They know when to flower, when to make the fruit. Seasonal. Okay. Similarly, we knew about grouting, cross breeding the plant, but we did not know that it is the DNA which is the root cause of that, and you can now do the biomedical,
Tissue
engineering. Okay. Now you come to the conclusion that look here, even the sexes need not meet in order to produce the offspring. So this lateral thinking is what causes science to progress faster.
Excellent.
And one of the important elements of that is how widely spread are these concepts accepted. If you do a textbook learning, this lateral thinking doesn't come.
Right.
I can give you one example to cut short.
Okay.
2500 years ago, one of the Buddhist monks is asked a question by his student. Sir, the daytime we get warm, earth gets warm because of the sunlight falling on us. The moon shines by reflecting the sunlight. So you have a black moon and a new moon. New moon and a, what is that?
Full moon.
Full moon. So, should we not have a difference in temperature on the earth, depending upon whether it is full moon or the dark moon? The monk thinks about it and he answers, you are partially right but partially wrong. What do you mean by that? He says, you stand under the shade of a tree. Do you feel the same warmth as same feeling that you stay outside? Because the environment modifies that, your ability to sense temperature. Similarly, it is true that the total amount of energy that is reflected by the moon should change the temperature of on the earth. But then you don't have a means of knowing the effect of that. A few months ago in the television interview about the warming up of the earth, global warming, there's a talk in which he says, by putting 25 satellites and looking at the radiation that is radiated from all over the globe, we will get the average temperature, and we monitor it for 20 years, we will know whether the average temperature goes up or not. However, this is still not sufficient if you want to measure the difference in temperature due to the full moon and the dark moon.
Okay. What are your current views, expectations, thoughts on the subject matter right now?
Well, look, I was it was brought to my attention by Srinivasan long ago, that what's his name, the French fellow?
Louis Carvan.
Carvan.
Yeah, we're talking about today.
Yeah, he brought to the attention saying that in biological growth, this seems to happen. The egg and the shell question.
Yes, calcium.
The calcium that gets accumulated on the shell. Does the hen eat so much of calcium to produce this much or not? Okay? I mean, this is again a lateral thinking. A reasoning which you, by looking at nature, you are trying to infer what it consequently means. The same thing happens in many other areas of biology. Similarly, if we can mindset saying that this low energy nuclear interactions are indeed feasible, there is nothing sacrosanct about abandoning this, because nuclear physics says they started with the accelerators. They first anchored on electromagnetic interaction and therefore repulsion and therefore high energy interaction.
Right.
You also know that there is a short range interaction which is very strong. Now how to bring these particles close together?
Right.
Therefore that we must be able to accept. In physics, I have always been puzzled by the fact there are nuclei like hafnium, which has got a cross section which is 20,000 bonds. That is 20,000 times the
Physical
area of the nucleus. That means it is able to attract a neutron which is far away. Okay, how do you account for it? Many teachers teach you different ways. One fellow is saying the lower the velocity of the neutron, the greater the time that it spends on the on the nucleus, and therefore it gets absorbed, which is nonsense.
I think it's very close to his theory.
Now, so there are similar areas. So what we ought to do is we must emphasize the fact that here is a short range interaction which Fermi sort of considered and say what is called Fermi contact terms. What do you call it? Fermi potential.
Impact parameter.
Impact parameter. Not impact parameter. He made a potential, which is Fermi potential. Right. Okay. So he shortened it so that quantum mechanically it could be solved. But it may not be there. Take for example gravitational potential.
Well,
we all thought it was 1 by r squared for law. But now there are experiments which proves no. It is not necessarily 1 by r squared.
One more term I think, isn't it?
Yeah, no, still, power of 6 or something. This Goribudru experiment. So, there are changes happening. I remember in my younger years, I asked a question to Meyer-Leibniz, a nuclear scientist from Germany. Why is it we can't put two neutrons at the same place? He said, no, they are Fermi particles, they can't be done. A condensation of two bosons is possible. Helium nuclei, they condense, therefore in the cold helium has got extraordinary property. It can creep, go up a wall of a beaker and flow back.
Alright.
Which is unthinkable in classical physics. Similarly, there are all this that we have learnt about the ranges of the nuclear of the forces and the way it varies with distance and the influence of the neighborhood on it can be changed. If you take plasma physics, now they say plasmas can be used to accelerate particles to GeV energy. All that you have is only electrons and protons. Okay, but still you can get electromagnetic field, which is GeV. Okay, now it took a long time for us to reach that, isn't it? Okay. We talk about it only now when probably plasma was known and the electrostatic forces, their ranges, etc. were all known.
So do you see cold fusion possibly taking a long time to resolve?
No, it's taking a long time, but at the same time I would say that look, your operational methods had changed in the early days.
Right.
Today, a university professor is more worried about the student getting his PhD than the student himself. I was told in the early years, the professor will give a problem to the student and it is up to the student to find the answer and see that he finishes it in 3 years or something.
Okay.
I think it was what is the name? Another physicist who said, now today the professor has to worry whether he will finish in 3 years or not.
So Rajan mentioned that yesterday.
Yeah. Okay. Now, all this shows that our method of doing science has considerably changed. It is what did the Columbia University fellows do? They heard somewhere that fission is feasible. It took them 2 days only. There is a meeting in Washington, and the fellow rushes to Columbia University and puts a foil there and sees whether he can observe fission, and he gets the result.
Okay.
Okay. Does this happen now? You have got to write a program, you have got to make a project, you put 50 copies of Xerox of your biodata before you get money to do any work.
Okay.
Isn't it true?
Sad but true.
It's a waste of money, waste of time. Even when I was director here, I used to tell them, we never made a 5-year plan. But today everybody says, oh, you have to wait for the next 5-year plan. When the cold fusion started, you may ask this question, how did India find money to support it? We never went to administration.
You already had what you needed.
We said, all right, you want to spend that? You spend it. You want to buy some equipment? Yes, you buy it. Because as long as the equipment is bought from India, that is from ESIL, supplied by ESIL, we had no problem. Cold fusion is not dead. One need not be ashamed of working on cold fusion. These are two things that has come from the West. That it is a self-defeating exercise. It is not. You may discover, if not cold fusion itself, but some technologies and some facts which are not at present known. For example, my friend K.P. Sinha, right?
Yeah. Oh yeah.
K.P. Sinha had a paper which he sent to me, that if you shine laser light on the surface of a metal, he showed that the electric field of the laser light can influence and cause cold fusion. There was a paper just sent to Current Science, they sent it to me for review. I said, you please publish it. Because that is another, what you may call, a lateral thinking process that is taking place. Today you see, for example, LEDs. People thought the efficiency of light production cannot exceed 2% or 3% or 5%. But today LED says 50%, and there is no limit. You can probably get much more. And once that happens, it has an economic value. You don't waste your electricity. You can save. So like that, I am sure that India is interested in that, and I would see that the youngsters get interested in this topic. We have the infrastructure. It is not something new that has to be equipment. You have to wait for the equipment to come. You go to BARC, I don't know, tomorrow
we are going there.
You are going there, you will see it's an expanse. We have put Brookhaven, Argonne together into one laboratory. We have disciplines as varied as biochemistry to metallurgy to engineering. No, it's always a pleasure. Because the most enthusiastic chap on cold fusion is Srinivasan.
Yeah,
he himself pays for himself to go and attend all the conferences. He comes back and gives talks, writes on newspaper.
Every time I try, but this time it seems to have time.
I know, even though you're retired, I want to wish you and your team here in the country great success.
I'm almost on my way out, but it's a pleasure to talk to you people, and I'm sure that Srinivasan will see to it that something is started in BARC, and the initiative that we had taken in 1989, which you
America provided, I think is flourishes.
Thank you.
Well, it's a pleasure and honor to have this time to speak.
Thank you
with
very much. Very nice.
Thank you, sir.
Thank you, sir.
Thank you.
Okay.